Okay, good morning. Welcome back. It's been so long. It's been like a week since we last met. Hopefully you've had a good week. You had a good weekend. Your days have gone well so far. I hope that for all of you. We are going to get started. We've got a good chunk of stuff to get through today. We're going to be covering section 6.3. With binomial and geometric random variables, and that will be the end of chapter 6. Okay, so just a couple things here before I jump into the lesson. Take a quick look in Canvas at our course. I've added a couple of things. So we're going to look at the modules. In this things you might need module, I've added a page on how to use table A. This has a couple of videos that I actually made last semester showing how to deal with z-scores, and then using table A specifically to find a value of z. Both have to do with how to utilize table A. And those types of things, which I think we need to make sure we are good at this point because it keeps coming up. So that's there in that module now. And also we have that quick link to the formula sheet and tables, which includes table A and formulas that you will be provided when you take the AP exam. I'll be adding the solutions to our Desmos activity from last week shortly. Haven't done that yet, but I should have. Right here in the chapter 6 assessment area, I've added some worked review free response questions. This is what I worked on yesterday. It is me walking through how to solve some free response questions based on what we've covered and what we're going to finish covering today in chapter 6. I believe there's 5 questions that I cover in it. All of them have multiple parts dealing with different things with random variables that we've covered in this chapter, and also dipping back into the previous chapter on probability. So this could be useful. I would recommend, if you're still looking for more examples, before you do the free response questions assessment, you might want to take a look at this video. It does end up being about 40 minutes long, all said and done. But again, there's 5 problems on it. So if you just want to look at one problem in particular, about 8 minutes or so for a problem. All right, so that is available as well. And lastly, on our Chapter 6 assessments, remember you have to do both of these assessments to gain access to Chapter 7 ahead of time before I unlock it next week when we start Chapter 7. And I'm working on the notes and resources for all of those sections still. The multiple choice is multiple choice. It is a quiz. The Chapter 6 free response question. I don't remember if I reviewed this with you guys or not. Can someone remind me if I talked about this last week or not? I don't remember for sure. All right, well, I'll jump into it real quick. So the free response question / self-assessment is similar to the self-assessment that we did the last semester for each chapter. This is done in the form of an assignment rather than a quiz, which is how I had it set up last semester. This is to give you more freedom in how you submit this task. Right? There are 2 sections, the free response questions and the self-assessment reflection section. Free response question here is comprised of 2 questions. The first question has to do with random variables, probability distributions, and combining random variables. The second question has to do with the binomial and geometric distributions and using those rules and formulas. So you have to answer both of those questions. If you want to do that in a Word document, Google document, type up your stuff. You can do that. If you want to do it all on a piece of paper, you can do that. It's entirely up to you how you would like to solve these problems. In the same submission, you have to complete section 2 as well. That is your self-assessed grade or level of understanding for the chapter based on the work that you've done, and then answering the reflection question. All right. You have freedom to choose how you want to submit these things. You can just do the text entry, right? You have a little drop down here to choose which submission type you would like to use, right? If you're doing text entry, you get the whole suite of like text tools, right? You can upload a picture, right? So if you want to take a picture of work that you've done by hand, add it to the text entry box, you're welcome to do that. You can upload documents, add a link to something, right? However you want to do that. Text entry has a lot of different options available. If you need help with those, just let me know. You also have the insert tab here. You can also choose to do a URL. So like if you're sharing the link for a Google document or something like that, you can do it this way. You can upload media. So if you want to record yourself answering the questions, you're welcome to do that. You can also attach a file. Remember, with the file upload, you can only upload one file. So that one file needs to contain all of your stuff. So if you're taking pictures of work that you've done by hand and all your answers to the questions, and it's multiple pages, all that needs to be compiled into a single document or a single file. Right? I would recommend using a scanning type app if you have one. There's lots of them available for free in like the App Store or Play Store, whatever your phone uses. There's free scanning apps, document scanning apps. Most of those will allow you to scan or take pictures of multiple pages and have those all be one file. Right? And that's what you need to use. All right. So there's plenty of options here. That's why I'm using this rather than the quiz, because the quiz I had to choose one of those. This way you can choose which one works best for you. And then when you're done, you submit. All right, and it has this little tracker here to show you what's going on, when it's been graded, all that fun stuff. All right, is there any questions about what I've got going on in the course? All right, also, if you notice, this says that it's due Friday, January 29th. That is this Friday. That is, again, just like last semester, this is for pacing purposes. I'm having it be due before we start chapter 7. Right? It doesn't mean that's the hard line in the sand, that you have to turn it in this Friday. Please don't feel that way. Take the time you need to be able to do this effectively and to the best of your ability. But for pacing and things like that, it's best to try and do it before we start chapter 7, but if you can't, it's fine. Do it when you can. You won't lose credit for it turning in late. Don't let these pile up though, because keep in mind, we're trying to cover 8 chapters this semester. You don't want to be left with a month left in school and have like 10 of these to do or 10 assessments between free response and multiple choice. That's a lot to do. Don't do that. All right. So there we have it. That's the up-to-date news on here. So with that, we'll jump into our lesson. If that wants to cooperate. If you have something you are writing notes with, now is the time to get that ready. There's going to be some things you probably want to have available in your notes for when you're doing the assessment or working on practice problems. Please have that prepared. Right? And as usual, if you need time to write stuff down, if you have questions, let me know. Raise your hand. Type it in the chat. I want to help. All right, so section 6.3 is on binomial and geometric random variables. All right, and this is again following along with our textbook, The Practice of Statistics, 5th edition. All right, today we're going to learn how to determine whether the conditions for using binomial or random variables are met. We're going to compute and interpret probabilities involving binomial distributions. We're going to calculate the mean and standard deviation of a binomial random variable, and then interpret these values in context. All right, we're going to find probabilities involving geometric or random variables, and when appropriate, we can use the normal approximation to the binomial distribution to calculate probabilities. All right. Note, this is not necessarily required for the AP exam, but it is part of our content. Okay, so this is what our goal is for today. It's going to be a good chunk of stuff. So first, binomial settings. What is a binomial setting? When the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen on each repetition. Right. Some random variables count the number of times the outcome of interest occurs in a fixed number of repetition. They are called binomial random variables. Right. The key thing that is different between the other random variables that we've looked at is that this is dealing with a fixed number of repetitions. It's not just simply counting the number of times something occurs. It's the number of times something occurs in a fixed set of repetitions or a fixed set of trials. All right. A binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. The four conditions for a binomial setting are the following. So again, these things you should have in your notes, these four conditions that you want to check to see if something fits into this binomial setting and if we can use binomial random variable to represent it. First, is it binary? Right, this means that the possible outcomes of each trial can be classified as a success or a failure. Right, essentially, you can have what you want or you don't get what you want. Right, is it binary? Number two, is it independent? Trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of another trial. This is the same definition of independence that we've used previously. Right? So again, we have to check this condition of independence for a binomial setting to be occurring. Right? Number. Right? And this is just in general, the number of trials n of the chance process must be fixed in advance. We don't just get to decide in the middle of running trials that, okay, now we're going to stop. This needs to be, okay, we're going to run 15 trials and record in each trial how many successes we have. Now that's fixed before we start. Right? That's what we need. And lastly, success. There must be the same probability P of success on each trial. This ties into the idea of independence. It's like flipping a coin, right? There's always a 50% chance of getting heads. That probability of success is always the same. We need a case like that where we know going into it, what's the probability of success? And it doesn't change. Right? To remember what these are, we use bins. Right? B-I-N-S, binary independent number success. This allows us to have kind of a system of checking that a binomial setting is occurring. Check your bins. All right. Can you please raise your hand if you need another moment to write this down? Okay. So, consider tossing a coin 10 times. Each toss gives either heads or tails. Knowing the outcome of one toss does not change the probability of an outcome on any other toss. If we define heads as a success, then P is the probability of a head and is 0.5 on any toss. The number of heads in n tosses is a binomial random variable x. The probability distribution of x is called a binomial distribution. The count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p, where n is the number of trials of the chance process and p is the probability of success on any one trial. The possible values of x are the whole numbers from 0 to n, right? If my trial, each trial consists of 5 tosses of a coin, right? Then I have a possible values of x from 0 to 5, 0, 1, 2, 3, 4, 5. I can't have more than 5 successes in any given trial because I'm only flipping the coin 5 times. Okay, so that's what that 0 to n represents. Okay. If you need a moment to write anything down, can you please raise your hand? In a binomial setting, we can define a random variable, say x, as the number of successes in n independent trials. We are interested in finding the probability distribution of x. So here we have an example. Each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count x of children with type O blood is a binomial random variable with n equals 5 trials and probability of p equals 0.25 of a success on each trial. Right. And it's important to keep in mind that in statistics, in these cases, when we say success, it's not denoting good or bad. It's just the outcome we're looking for is considered a success. Right. In this setting, a child with type O blood is a success, S, and a child with another blood type is a failure, F. So what's the probability that we have exactly 2 kids with type O blood out of the 5? Or P of x equals 2. This is the probability of 2 kids, 2 successes, and 3 failures. This is representing the outcome of the first 2 kids having type O blood and the next 3 all not having type O. We would get 0.25 times 0.25, right? Times 0.75, 0.75, 0.75, right? And we could kind of look at this in a tree diagram if we wanted, right? We have a child born, they have success or fail. Then after that one, success or fail, and we can follow that tree diagram and we get this multiplication. Right? We have 0.25 squared times 0.75 to the 3rd power, or cubed, and we get 0.02637. Now, we're not done, because out of 5 kids, there's more than one way for 2 of them to have type O blood. We could have the first 2 kids have type O. That's one way. There are 10 possible ways to be successful. All right? And we have them listed here. This would essentially be our outcome space. Right? We could verify that each of these arrangements has the same probability as the one we already calculated, 0.02637. And that's because of rules of multiplication. Right? Doesn't matter the order in which we multiply these things, we'll end up with the same equation. Right? So we have 10 possible ways to get that result, which means we have to multiply that result by 10. Right? So the probability of x equaling 2 is 10 times the probability of one of those outcomes occurring, which all have the same probability, and we get 0.2637, about 26%. Is there anything I can clarify here so far? Does anyone need a moment to write anything down? Okay. Note, in the previous example, any one arrangement of two S's and three F's had the same probability. This is true because no matter what arrangement, we'd multiply together 0.25 twice and 0.75 3 times. We can generalize this for any setting in which we are interested in k successes and n trials. Right? That is, probability of x equaling k is equal to the probability of exactly k successes in n trials, which equals the number of arrangements times the probability of success to the k power times the probability of failure to the n minus k power. Right, essentially k, number of successes, n minus k is again the number of failures. Right, so the success to the power of number of successes, failures to the power of number of failures. Right. The number of ways of arranging k successes among n observations is given by the binomial coefficient. All right. This here, this nk in the tall parentheses is read n choose k. Right. And it is equal to the fraction n factorial divided by k factorial times n minus k factorial. Right. In math, yes, we've given a meaning to the exclamation mark. It means factorial, and it's defined like this here for k equals 0, 1, 2, and up to n, where n factorial equals n times n minus 1 times n minus 2, on and on until we get 3 times 2 times 1, and now we're out of numbers. Right? And 0 factorial equals 1. It does not equal 0. Right? There's reasons for that. We don't have time to get into that in this class. It's beyond the scope of this class. Just know that it's a fact. So an example of a factorial, right? If I do 5 factorial, it's 5 times 4 times 3 times 2 times 1. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? It says whichever number is next to the exclamation mark, start with that one and multiply by each number that's less than that whole number. Right? And that's factorial. You can also have your calculator do this work for you, right? And that is you go to the math button, right? It's under the alpha button. Scroll over to probability, PRB, and you see NCR, that's the command, right? That says N choose R, right? So we can click to the third option here, hit enter. Now the first number, right, needs to be in front of NCR. So if we want to say 5, oops, it deleted my stuff because that's annoying. We'll get back. Got to put in that number first. I always forget. 5 choose 2, which is the scenario we just had. We get 10, which matches what we've saw on the previous slide. If there's 5 trials there, and we want to choose 2 successes, there's 10 possible ways to have 2 successes in 5 trials. Right, so we can have our calculator do this calculation, which is kind of nice. Right. We don't have to do it by hand. We don't have to use this formula unless we really want to. For this class, there's probably no reason to really use that formula unless you really want to, if you can do it on your calculator. All right. Does anyone need a moment to write anything down on this slide? Okay. So then, the binomial probability formula. This is what we're working towards. The binomial coefficient counts the number of different ways in which k successes can be arranged among n trials. The binomial probability of p x equals k is this count multiplied by the probability of any one specific arrangement of the k successes. If x has a binomial distribution with n trials and probability p of success on each trial, the possible values of x are 0, 1, 2, up to n. If k is any one of these values, then the probability of x equaling k equals n choose k times the probability of success to the power of number of successes times probability of failure to the power of number of failures. Okay. And you see this, right? This tells us the number of arrangements of k successes. That's our n choose k. Probability of k successes, probability of n minus k failures. Right? That's what these two exponents tell us. Right? Is there anything I can clarify so far? Can you please raise your hand if you need another moment to write anything down? Okay. So then, how to find binomial probabilities? We have some steps. Step 1. State the distribution and the values of interest. Specify a binomial distribution with the number of trials n, success probability p, and the values of the variable clearly defined. Right? Don't use things without saying what they are first. Don't just like have a problem and be like, okay, p of x equals 7, without first saying, okay, x is going to represent da-da-da. I want to know, you know, how long or what's the probability of having 7 successes. Probability of success is this. Then you can start using all those things. Right? Show that somewhere in your work and in your calculations. Step 2, perform calculations. Show your work. Do one of the following. Use the binomial probability formula to find the desired probability from the previous screen, or use your calculator. Right? There are 2 commands in your calculator, binom PDF and binom CDF, and you need to make sure to label each of these inputs. I'll kind of demonstrate what that is momentarily. All right, step 3, answer the question that you were asked. So, in your calculator, let's clear that out. All right. In your calculator, if you click second and then vars, where above it says distr, distribution, you get this menu. There's a lot of things in here. We want to click up because it takes us to the end of the menu. And we're looking at binom PDF, binom CDF. All right. These do calculations for us. So option A here is binomial PDF. Right? What that does is it calculates the probability that x equals exactly k successes. Binom CDF calculates the probability that x is less than or equal to k successes. Right, so one gives us exactly number of successes, one gives us less than or equal to that number of successes. Right? And in each of these, you must enter the correct parameters, as they would say in math speak. Right? Your calculator has this set up kind of nicely for you. How many trials? Right? We'll use our blood type. We had 5. Probability of success was 0.25. We wanted to know probability of 2 successes. Right? So n equals 5, p equals 0.25, k, in this case, they're saying x value is 2. Let enter. It's got our stuff in here. Enter again. And we get the same probability that we saw previously, about 26%, 0.26367, blah, 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 blah. Right, so that does the calculation for me. If I wanted to know what's the probability of having 2 or fewer children with blood type O, we would do the same set of keystrokes here, except instead of using the PDF function, we'll use option B here, which is binom CDF. It's going to ask for the same 3 numbers, right? 5 trials, probability of success, 0.25, the value of k, all right, the value that's in my probability statement there, p of x being less than or equal to 2, goes in for X value. And we get 0.89. So this tells us the probability of having 2 or fewer kids with blood type O, right? Almost 90%. Okay. So that's how we can kind of use our calculator, which is nice. So now what this means by label each of the inputs, if you're going to use technology, which means you're not going to have the math work to show, right? You must label things, right? So that means, so here real quick, the binomial PDF, that gives us the probability of X equaling K. CDF is the probability of X less than or equal to K, right? Now for labeling, if we're going through work and it says, hey, find the probability of this and this in this binomial distribution, you will use, you'll say like, okay, well, I use the binomial PDF function with n equals 5 trials, probability of success of 0.25, and K equals 2. This is what it means by labeling, right? Having these things here. It's not enough just to say I used binomial PDF and I got the result. They want to see that you understand what the parameters are and what things you need to be considering to find the solution. All right, so that's what it means by label each of the inputs. Is there anything I can clarify on this? Okay. So now, finding binomial probabilities. So same context as before, except now we want to find the probability that exactly 3 of the children have type O blood. All right, so X will be the number of children with type O blood. We know X has a binomial distribution with n equals 5 and P equals 0.25. Okay, so again, I'm labeling and identifying the things I'm going to use. Right, and we say probability of X equaling 3 is equal to 5 choose 3 times 0.25 to the third times 0.75 squared, which equals 10 times 0.25 cubed times 0.75 squared equals 0.08789. Okay. So again, they've shown the work here. And again, we could do this in the calculator using the binomial PDF function. B, should the parents be surprised if more than 3 of their children have blood type O? To answer this, we need to find the probability of X being greater than 3. We're using the same set of variables and such, so we can get right to work. Probability of X being greater than 3 is equal to the probability of X equaling 4 and X equaling 5. So we add these probabilities, right, and we get all this math, which results in 0.01563, and about 1.5%. Since there is only a 1.5% chance that more than 3 children out of 5 would have blood type O, the parents should be surprised. Right, so we're using this result to justify our answer. Does anyone need a moment to write anything down from this screen? Right, and is there anything I can clarify? We can also calculate mean and standard deviation of a binomial distribution. We can describe the probability distribution of a binomial random variable, just like any other distribution, looking at the shape, center, and spread. We'll consider the probability distribution of X equaling the number of children with blood type O in a family of 5 children. So we've got our histogram and we've got our table. Both are representations of the probability distribution. We get a shape. The probability distribution of X is skewed to the right. It is more likely to have 0, 1, or 2 children with blood type O than a larger value. Center, the median number of children with blood type O is 1, based on our formula for the mean. We get a mean of 1.25. Again, this is the formula for mean that we've used throughout this chapter, right? The mean is equal to that outcome times the probability of that outcome plus second outcome times probability of second outcome, and so on. We only have 5 possible outcomes, so there's that calculation. The spread, right, the variance of X is given by this mess of a calculation, which is again the difference between the outcome minus the mean squared times probability of that outcome, right? And we do all of the outcomes. We get 0.9375, which results in a standard deviation of about 0.968. Now, knowing how to do all these calculations is well and good, and they will work for binomial distribution. However, we have a shortcut that saves us a ton of time and calculation effort. But before I show that, does anyone need a moment to write stuff down from this slide? Okay. Here's the shortcut. The mean and standard deviation of a binomial and random variable. If a count X has a binomial distribution with number of trials N and probability of success P, the mean and standard deviation of X are mean equals NP, or N times P. Right, so number of trials times probability of success. Standard deviation is the square root of number of trials times probability of success times the probability of failure. Right, NP times 1 minus P, which also implies NP times 1 minus P is the variance, because the square root of the variance equals standard deviation. Please note, these formulas work only for binomial distributions. They can't be used for other distributions. If you have a normal distribution, right? If you have, just something that we haven't considered binomial, this will not work. Use your other calculations. You can see the calculation for mean and variance that we used for other random variables works on binomial. It does not go the other way around. Okay. Is there anything I can clarify about that? Right. Does anyone need a moment to write these down for their notes? Okay. So an example. Right. Mr. Ballard's 21 AP Stats students did the activity on page 340. Right. This is having to do with tasting the difference between tap water and bottled water. If we assume the students in his class cannot tell tap water from bottled water, then each has a 1 in 3 chance of correctly identifying the different types of water by guessing. Right. Let X equal the number of students who correctly identify the cup containing the different type of water. Right, and we're going to find the mean and standard deviation of X. Since X is a binomial random variable with parameters N equals 21 and P equals 1/3, we can use the formulas for the mean and standard deviation of a binomial random variable. And again, when doing a problem like this, you may be asked to first explain why this is a binomial random variable, in which case you'd have to check bins. Make sure it's binary, it's independent, there's a fixed number of trials, and there's a consistent probability of success. Okay. This fits all those things, so we're good to go. we get a mean of 21 times 1/3, or 7. Right, this means we'd expect about 1/3 of his 21 students, about 7, to guess correctly. The standard deviation ends up being 2.16. Right, so if the activity were repeated many times with groups of 21 students who were just guessing, the number of correct identifications would differ from 7 by an average of 2.16. Right. Is there any questions? Can you raise your hand if you need another moment to write anything down? The binomial distributions are important in statistics when we wish to make inferences about the proportion P of successes in a population. Almost all real-world sampling, such as taken in SRS, simple random sample, from a population of interest, is done without replacement. However, sampling without replacement leads to a violation of the independence condition. This could be a problem. When the population is much larger than the sample, a count of successes in an SRS of size n has approximately the binomial distribution, with n equal to the sample size and p equal to the proportion of successes in the population. All right, so if we're dealing with a very large population, right, then we might be able to use a binomial distribution to approximate probabilities. Right, this brings us to our 10% condition. When taking an SRS of size n from a population of size capital N, right, we can use a binomial distribution to model the count of successes in the sample as long as n is less than or equal to 1/10 of capital N, meaning that the size of our sample must be less than or equal to 10% of the entire population we are sampling. If that's true, then we can use a binomial distribution to approximate chances of success, which is nice because that allows us to do something else with our data. All right. So again, this is our 10% condition. Okay. So we need a moment to write anything down from this slide. Okay. Is there anything I can clarify? So we can also use normal approximations for binomial distributions, right? And this is as n gets larger, so our sample size gets larger, something interesting happens to the shape of a binomial distribution. The figures below show histograms of binomial distributions for different values of n and p. What do we notice? First probability is slightly skewed to the left. We have a sample of 10, probability of 0.8. Next one is a sample size of 20, probability of 0.8, slightly less skewed. Finally, a sample size of 50, same probability of success of 0.8, and we get something that looks approximately normal. Okay, so as n gets larger, the sample size, the number of trials gets larger, we approach something that's approximately normal. So this leads us to the large counts condition. So this goes for something that's already satisfied the 10% condition. Right. We can then check the large counts condition to see if I can use a normal approximation on a binomial distribution. Suppose that X has the binomial distribution with n trials and success probability P. When n is large, the distribution of X is approximately normal with mean and standard deviation found the same way we just did for binomial distributions. Mean of X is NP, standard deviation of X is NP times 1 minus P, and take the square root of that. As a rule of thumb, we will use the normal approximation when n is so large that NP is greater than or equal to 10, and n times 1 minus P is greater than or equal to 10. That is, the expected number of successes and failures are both at least 10. All right. When this occurs, then I can use a normal approximation, table A, all the things we know about a density, a normal density curve, to calculate probabilities using the mean and standard deviation of a binomial distribution. Right. And this can be very helpful. We're not specifically going to see an example of this, but I do have a worked example in some of the problems that I've done. So we need a moment to write any of this down. So then we get into our geometric settings. So we just completed binomial, now we're doing geometric. In a binomial setting, the number of trials n is fixed, and the binomial random variable x counts the number of successes. In other situations, the goal is to repeat a chance behavior until a success occurs. Right? These situations are called geometric settings. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability P of success must be the same. Right? So in other words, we're going from a fixed number of trials and a fixed probability of success to, now I don't know how many trials it's going to take, but I'm going to record how long it takes before I get a success. Right? But I have a fixed probability of success. Right, so that becomes geometric. Right. Excuse me. So we need a moment to write any of this down. In a geometric setting, if we define the random variable y to be the number of trials needed to get the first success, then y is called a geometric random variable. Probability distribution of y is called a geometric distribution. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. Probability distribution of y is a geometric distribution with parameter p, probability of success, on any trial. The possible values of y are 1, 2, 3, up through about infinity, because we could just have really bad luck and never get a success. Right? It's very unlikely, but mildly possible. Like binomial random variables, it is important to be able to distinguish situations in which the geometric distribution does and doesn't apply. Right? In this case, kind of the key thing we're looking for is, how long does it take to get one success? What's the probability of getting our first success in 3 trials? Right, that becomes geometric. Does anyone need a moment to write anything down from this screen? Okay. So let's look at an example for a geometric probability. We're going to consider the lucky day game. The context of this game is that a teacher is going to give 10 homework problems. As an alternative, they offer to the class that they can play the lucky day game. In this game, a student will be selected at random from the class and asked to pick a day of the week. Right? So they have 7 options. Then the teacher will use technology to randomly choose a day of the week as the lucky day. Right? If the student picks the correct day, the class will only have 1 homework problem. If the student picks wrong, a teacher will select another random student who will then choose another random day of the week, and the teacher will then randomly choose another lucky day. If the guess is correct, then the class will have 2 homework problems. Right? This game continues until a student correctly guesses the lucky day. Right? The teacher will assign a number of homework problems that is equal to the total number of guesses made by members in the class. Right? So that's the context of this game. Right, so the random variable of interest in this game is y, which equals the number of guesses it takes to correctly match the lucky day. We want to know, what is the probability the first student guesses correctly? The second, third. What's the probability the kth student guesses correctly? Right, so we see the probability that the first student guesses correct is 1 in 7. Right, they're picking a day at random. There is a 1 in 7 chance that they pick the correct day because there's only 7 days to choose from. Probability of the second student guessing correctly, which means the first one is incorrect, so then the second one is correct, is the probability of 1 incorrect answer, 6 out of 7, times probability of correct answer, 1 out of 7. We get 0.1224. For 3, right, that means the third guess was correct, the first 2 were incorrect, is 2 incorrect answers times 1 correct answer, we get 0.1050. So essentially this keeps building incorrect answers, and the last multiplication will be probability of correct answer. So we'll always only have 1 multiplication of probability of correct, and then we just keep multiplying incorrect. So we get the geometric probability formula from this concept. If y has the geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, up through infinity. If k is any one of these values, then the probability of y equaling k equals probability of failure to the power of 1 less than number of trials for success, right, k, times probability of success. So we use this. Compared to the other formulas we've seen, a relatively simple formula. Failures multiplied a bunch of times 1 probability of success. So we need a moment to write this down for their notes. Okay. So then that gives us, we get this distribution. We've got a probability distribution, we've got the histogram, and we've got the beginnings of the table. We can't show the entire distribution because the number of trials it takes to get the first success could be an incredibly large number, right? There's nothing saying it doesn't take 40 tries or 50 or 60. It'd be really bad luck, but could happen. So these aren't necessarily complete, but it gives us enough of a picture. Right, we see that this is heavily right skewed, and this is characteristic of any geometric distribution because the most likely value is 1. Right? The most likely thing to happen is that the first guess is correct in the scenario where we have, the lucky day game. The center, right, the mean of y is 7, and we'd expect it to take 7 guesses to get our first success. We'll show the calculation for this in a moment. The spread, the standard deviation of y is 6.48. If the class played the lucky day game many times, the number of homework problems the students receive would differ from 7 by an average of 6.48. It's got a really big swing. And we get this rule, right? The mean or expected value of a geometric random variable. For right now, we're not worrying about how to calculate the standard deviation for a geometric random variable. We're just considering the mean. If y is a geometric random variable with probability p of success on each trial, then its mean or expected value is 1 divided by p. Right, so kind of the most basic formula we've gotten so far for the mean, 1 over p. Right? So in this case, we get the mean of 7 because 1 divided by 1/7 is 7. Right. We can also calculate probabilities, geometric random variable probabilities, using our calculator. Going through the same kind of set of button presses we did for the binomial CDF, we have geometric CDF and PDF. We go second, vars, we get distribution. We'll click up, and it's option E and F. We get geomet PDF, which is the probability of y equaling k. So y, what's the probability it takes 3 trials to get the first success, right? That would be PDF. And in these cases, the parameters will be the probability of success and number of trials to get first success. So in this case, there is no n. We don't have to enter the total number of trials because we don't know. Right. Then the geomet CDF, that is for the probability of y being less than or equal to k. Right, so what are the chances that it takes 3 or fewer trials to get the first success? Right, so in that case, we would use CDF with the same 2 parameters. Right, so we do have some help in our calculator to do those types of calculations. Is there anything I can clarify? That brings us to the end of the notes, right? The binomial and geometric random variables, right? So we've covered all of these things. We determined whether the conditions for using a binomial random variable are met. We looked at how to compute and interpret probabilities involving binomial distributions. We can calculate the mean and standard deviation of binomial random variable, and hopefully we can interpret these values in context. We can find probabilities involving geometric random variables, and we discussed the possibility of using a normal approximation with a binomial distribution to calculate probabilities. Right? There's the 10% and large counts condition that we need to check for. Right? And that brings us to the end of our slideshow. So, with that, that is the end of chapter 6 on random variables. Unfortunately, this week I only get to see you guys once. We do not have the day to have practice exercises in class. I will be completing a Desmos activity for section 6.3. That will be an opportunity for you to practice. It will not be assigned. It will not be you will not have to do it to get credit or anything like that, as the previous one was, because we don't have time to do it in class. It will just be made available so that you can practice if you like. Other than that, I heavily recommend trying the practice problems for section 6.3 that are in the Canvas module for chapter 6 to see if you can make sense of those and get the right answers. And if not, you can ask for help, and I can help you out with those and help further your understanding. You should start working on the assessments for chapter 6. Like I said, they are scheduled as due on Friday. Please don't take that as a hard set line. It's just because I want them to be due before we start chapter 7. Please get to them and submit them when you feel prepared to do so. All right, you should, if you feel like you're not able to complete them, get some more practice in, ask for some help, and then do them.